So now let's look at the review on rockets and gravitational acceleration used with orbits. The first problem is an astronaut orbiting the Earth inside the space shuttle floats in air. He is, 1, not accelerating, 2, accelerating directly towards the center of the Earth, 3, accelerating in the direction of the orbital motion, 4, accelerating opposite the direction of the orbital motion. And so, again, just like any other orbit, right? What you've got is a space shuttle, which is in orbit around the Earth. And so, as a result, since this is the center of the Earth, it's moving in a circle of, some radius. And so, naturally, since it's moving in a circle, then what you know is that there has to be a centripetal acceleration towards the center of the Earth, which means that there has to be some force. And the force that causes that is the attraction that it has towards the center of the Earth. This is actually kind of drawn not to scale. Most of the orbits for the space shuttle are much lower Earth orbit than this. This one looks like it's one Earth radius above the Earth's surface. In which case, then the gravitational acceleration would be 1/4 of what it was on the Earth. And again, remember that the gravitational force is G, then it has the mass of the Earth, the mass of the rocket, divided by r squared, where that's the distance to the center of the Earth. So if r is at the surface, then it's our usual, mg type weight that you'd see if you were 1 Earth radii above the Earth's surface, then it'd be 1/4 of what it was. But this usually the space shuttle is at much lower Earth orbits than that, so it's actually only a small effect. But again, the idea is that clearly it is accelerating. You can get rid of that. It's not accelerating in the direction of orbital motion because it's going around at a constant speed. It probably orbits every 20 minutes. The Earth accelerates opposite the orbital motion. Nah, and so it has to be this one, which is accelerating directly towards the center of the Earth. Now, let's look at the second one. To propel itself forward, a rocket pushes against 1, its own exhaust, 2, the air through which it travels, 3, the launch pad, 4, the Earth. And again, as we talked about it before, is if you have a rocket ship, right, almost all of the mass of the rocket ship is actually the fuel that's inside. And so the rocket ship actually usually is only a small fraction of the mass of the fuel. And so the reason why the rocket goes forward at some high rate of speed is because you're shoving the fuel out the engine at a fairly large rate of speed. And so the spaceship goes larger because the fuel is so massive. So again, the idea is it doesn't push on the air. It doesn't push on the launch pad. It may be out in outer space, and it certainly doesn't push on the Earth. So the only thing is that it pushes basically on the fuel as it shoves it out the back end. Third one. While an astronaut is making a spacewalk near the space shuttle, 1, he has 0 weight and therefore feels weightless. 2, he has only a microgravity weight, so he feels almost weightless. 3, he has a large weight but feels weightless because he's falling. 4, he has a large weight but he is not accelerating, so he feels weightless. And so, just like the previous picture, you have the space shuttle orbiting the Earth, and again, this is a really accentuated picture. So 1 Earth orbit, that's the Earth's radius. So here's the Earth, and so the idea is that the space shuttle only is it's probably only just a little bit above the Earth's surface. It's about 100 kilometers. It's a small fraction of the Earth's radius, and so the space. This man that's on a spacewalk outside, he's also moving in a circle, and so there still has to be this centripetal acceleration, which means that that's caused by the attraction to the Earth. So clearly he doesn't have 0 weight. He's got to have an attraction to the Earth in order to keep moving in a circle. and he's not at many Earth radii away, and so he doesn't have a microgravity weight. And his weight's pretty appreciable, pretty close to what it is on the Earth, but he feels weightless because he's falling. And he's clearly accelerating because he's moving in a circle. So there's no question that 3 is the right answer. All right, fourth one. The weight of an astronaut on a spacewalk outside the Earth orbiting space station is 1. The same as her weight on the Earth's surface. 2. 0. 3. Slightly less than her weight on the Earth's surface. 4. Slightly more than 0. And so the same picture applies. So as you know now, it says that clearly its weight's not 0. Weight's not small. And clearly the weight's slightly less because it is above the Earth's surface, probably a bit. But slightly less. Might be 90% of her weight on the Earth. So 3 is definitely the right answer for this one. So that ends the discussion about the review about rockets and gravitational accelerations.